Hello everyone, session 15 today, and we're going to be talking about joint design. If you remember last time we kind of emphasized how important joint stiffness was in the performance of the side frame, and we just quantified joint performance by a single number, the joint stiffness. And now what we're going to do is look at, well, what design elements make up a good joint. So we're going to kind of go back to the earlier part of the semester where we were talking about body structure elements, and now kind of pick up this this other element, the joint. When we talk about joint performance, we can really look at them in two different ways. The first is called in-plane loading of the joint, and this is kind of what we were assuming in the last lecture. So we have two beams here. They define a plane, and we're looking at the motion of the joint within that plane. So we're kind of applying a moment in this direction, so that the beams kind of flex still within that plane. So that is one way to load a joint, and that's the joint stiffness that we were looking at before. There's a second way. It is kind of less important, but not totally unimportant, and that's out-of-plane bending. So here again is the same two beams that we were looking at before and the plane that defines them, but now we're loading the beam perpendicular to that plane. So this is called out-of-plane loading of the joint. This tends to be more significant in twisting of the body structure. The in-plane loading tends to be more important in bending of the body structure. So what we're going to be looking at in the subsequent slides are primarily this idea of in-plane loading. So let's just simplify the problem a little bit. We're going to consider two beams coming together. This might be like a B-pillar, and this might be the rocker section. And initially what we're going to be looking at is that there's a difference between the width of these two rectangular sections. Okay? So again, these are hollow sections, thin wall sections that we're looking at. And what we're kind of going to say is we're kind of restraining this here and here, and we're applying a force, or it could be a moment here at the B-pillar. Okay? And there's a little difference here. This width is smaller than this width. And we know from our studies earlier about plate buckling that for thin wall structures, when we apply a force or a moment, here's a plate here, that most of the loading will occur at the corners. And we'll have not only the corner loading here from the direct stress, but in the case of a force, we'll have some shearing stress that we need to generate here. And one way to kind of idealize this is to say, well, when we apply a load like this, all of the direct stress will be input at the corners of the section, and all of the shearing stress will just be along the web edges. Okay? So the corners and the edges carry the load. We know that from kind of a simplification of what we had done before with our simple structural surface models. Okay? So let's take a look at this case. And again, we're kind of looking at a case where there's a difference between the width of the two beams. Okay? So here is looking at the end view of this beam, view down the axis of the beam. Here's the axis. So we have this difference here between W1 and W2. So what that means is that the loads that are coming in here are appearing at the corners of the beam, and they're being applied to essentially a flat plate. And we saw before how poor a flat plate was a flat plate was in reacting normal loads. Okay? Kind of going to get some deformation like that. Okay, so what we're looking at here is kind of, we're starting with a really bad condition. So this would be a very inefficient and very flexible beam. Okay? And I think we can show this effectively with this little video here. So I have a plastic model of this case. This and this area are constrained, and I'll be applying a force at the top of the B-pillar section here. So let's take a look at that. So here you can see all the deformation that's occurring at that flat plate. That's this top portion of the rocker. So this is in-plane bending. Now this is a case of out-of-plane bending, so now we're loading it perpendicular. But again, you can see lots of distortion that's occurring, primarily because of this little offset that we have here in this particular case. Okay. So kind of rule number one is we want to avoid this offset if we want to have a good joint. So here is kind of an improvement here. Here now we've made W1 and W2 equal. So now we have essentially a plane, this yellow plane, to transfer loads more in shear than in this direct stress that we were getting before in this case. That was really what was killing us there. So let's do what we did when we looked at the body and bending. And flowing down requirements. If you remember, we idealized the structure with some simple structural members. So we're going to use the same ones, bars and surface elements. So here's a surface element, and here's the load that we're applying. So we saw that surface element could only be loaded by loads in its plane. So here's the applied load on the top here. So we need to generate these edge forces. And now we needed a place to react those, so we're going to add a bar. So this bar represents the corner of this upper member. And if you remember, the bar element can only react loads down its axis. So here we kind of have a shearing on it going down its axis, and then we have to generate some reaction force here. We're not showing it yet. So we need a bar in the back. And we'll need a bar at the bottom. So now we've reacted each one of these with an equal and opposite force. So here we need a member to react this force. So we've added a bar element here. And if we look at our joint, there's really not anything there, but we see by a free body diagram that we need something there to react those loads. We had an unbalanced force here, so we're going to add a shear member, so that makes sense here. We kind of have this wall here, and that generates these forces. So this one kind of pushes back there. And then we can complete that by putting in a shear member at the front and the end. Okay, so let me get rid of all my little marks here. So what we now have is a set of load paths that are efficient to react this applied load. Okay? And we know it's going to be relatively efficient because we've made this surface to be uniform, this yellow surface that we've drawn. Okay? So this will be a better joint than the one that we saw in the movie. So it's natural to say, well, this is going to be a known applied force. How big is this force here? How big is this force here and here, etc.? Okay, and we saw the way to do that is to, take this and explode it, and then do free body diagrams on each element. And what we can do is then find out, using a free body diagram, what are these forces, given that as the input force. Once we have this one done, we can look at this bar, because now we know what this one is, and we can kind of cascade through the whole system. Okay, so just for your notes, this is what's been done here. So for example, panel D is this one. And here is the equilibrium equations for that. So given F is an input, how big is this? Are these shear loads X sub D? They're given by that amount. Here is bar S1. Bar S1 is this one. So here's the free body diagram on it. Okay. So again, just for your notes, we're not going to go through this in any detail. And then here are the remaining elements. So now the objective of this little exercise was to say, well, if we know how big this applied force is, how big are the forces flowing through the different elements of this joint? Okay. And what we find from this analysis is that there's two that are particularly important. This little bar S3 right here, these are very big loads, so this is very large. And the shear panel B, okay, and again, these are also very large. Okay, so these are the highly loaded areas of this little joint, and one of the bad things here, this bar 3 is loaded in compression, so it will tend to buckle, and this is in shear, so it can tend to shear buckle. Okay, so let's take a look at these in a little more detail. Here is the bar element here. We have a compressive load, like I mentioned, so it's going to be prone to buckle. The load is inversely proportional to W. W is this dimension here for how wide that top beam is. Okay? So as we increase W, we'll be reducing the forces in this little bar. So we're going to come back to that. That's going to be an important design principle for good joints. When we look at the little intersection of the two beams, kind of where this beam comes into that beam, we have this little shear element. And again, the shear flow, here's shear flow, is inversely proportional to W as well. Okay? And W is the width, how wide is this top beam as let's draw it like this. Here's W. So as W goes up, the loads on both of these elements go down. Okay, so just make a note of that. Okay, so let's take a look at this, and here's a little animation. So this is a little FEA model. We're loading it in this direction forward now in this picture, and I want you to kind of look at what's happening by this little bar right in this area here, and what's happening in the shear area here. To try to kind of separate these out, and I'll play this again in a minute. And again, what we're going to be looking at here in the colored highlights is the deformation of this section. And by the way, this is being supported here and here, like that. So let me just get that out of the way. Okay. So you see that this is kind of buckling, this shear panel here, and we're compressing this right in here. So that area has buckled. Let me play it again. So this area here will start to see the buckle, and then we have diagonal buckles here. Okay, and this kind of loading is very consistent with our little analysis that we did here. Okay, so my point here is that even though we've made this joint a lot better by making this surface continuous now, it's in one plane, it doesn't have that offset that we had at the beginning, we still have some kind of issues with this joint. It's better than the one that we looked at the beginning of the lecture, but still not as good as it could be. Okay, so how could we kind of analyze this? Well, you know, one thing is for this this member here being loaded like this, it's loaded in shear. We know from our plate buckling equations that we have a case of shear buckling, and that's what we saw in the video. So how can we improve that? And generally the way that we can do that without adding mass is to just add some beads. Okay, so here is a case where we've added some diagonal beads here to inhibit the shear buckling, and we've added some beads here to kind of inhibit that resistance to that compressive force that we got here. Okay, so now this is kind of the second level of improving a joint. Once that we've made these elements in the same plane, then we can add these beads in order to improve the performance in those areas. Okay? There's other ways we could do it, but these are the ones that would add very little mass at all. Now the other thing that we can do, we saw that both of these loads, the shearing loads that were being applied to this area and the magnitude of the compressive loads that were being applied there were inversely proportional to the width here. So one thing that we can do is just make that width bigger. And as we saw in the last lecture, the overall width of that section is highly constrained, so we just can't have a really wide B-pillar. But what we can do is right at the base, we can put a big radii in there like this. So effectively what we're doing is taking this width that was rather small initially, and we're increasing it to a much wider width, and that reduces those loads as you would expect. Okay? So this is kind of a third area. This was a second area of improvement, and then the first was making the shear walls in the same plane. Okay? So let's take a look at kind of at these improvements. Here was the kind of the untreated case. We had buckling occurring here and buckling occurring here. We've added our beads, we've increased the radius here, and now we get a case that looks kind of more like a normal section where we have much less deformation occurring at the joint itself. Okay. So these beads are the most mass efficient way to do this. There's other ways to do that, and remember we're trying to provide a load path here, and we're trying to prevent buckling here. Okay. So in the next slide shows some improvements to joints. This was from a Japan Society of Automotive Engineering paper here, and we're looking at different ways to improve in-plane bending. All the joints have the shear walls aligned, so that's the starting point. And that stiffness of the base joint untreated, but with the shear walls aligned is unity. And here we have some through-section bulkheads. Again, we're adding mass, but what we're doing is we're applying or defining a good load path to take those compressive forces. So we get almost a doubling of the rigidity of the joint. Here we're adding a doubler plates on the shear wall. So here we're trying to improve that shearing in this area by just making the wall thicker. And again, that's independently of the first change. This would also be worth a doubling. And then here is adding the radii alone. So each one of these elements by itself essentially will double the rigidity. Okay, so these are different ways to do it. These two add more mass than just an intelligent placement of beads. Okay, so let's try to quantify this and see how good we can really get. So this is going to be a series of plastic model tests that were done, and the first one is starting with the terrible condition where we don't have any of these improvements, even to the extent as we have this offset wall here. And what you'll see is using our little tensile test machine here. So we have a load applicator where we can measure force, we can measure deformation at the point of load application, and then in the little screen here we can get a load deflection curve. Okay, and the steeper that is, the more rigid the joint. Okay, so let's take a look at this first one. This will be the worst case. So here's our joint. Now we're applying the load, and you can see that this is kind of not, the beam isn't bending at all. It's like a rigid bar, and all of the deformation is in the joint. Okay, and here this colored line is an indication of the slope of the line. This is force and deformation here. Okay, so again, we want that to be as kind of a high slope as possible. So here we just align the surface of one side. I won't go through the video here, but you can kind of see that this slope here of the colored line is much greater than this slope. So you can get kind of an idea of the order of magnitude improvements. Here in the next one, we've aligned the shear walls on both sides so that even though we can't see the opposite side here, we've got both shear walls aligned. And you can see this is really, pretty dramatically different from where we started. This, by the way, this is a reference here that's the same on all of these plots. And in this last one, what we'll do is we're going to add the radii. Okay, so you can kind of see the relative performance here as we add each one of these things successfully. We have a very dramatically different performance of the joint here. So let's just take a look at this last one. And if you remember the first one that I showed, basically when we were pushing on that, what would be the B-pillar beam, the little horizontal beam, it looked like that was perfectly rigid. It wasn't flexing at all because all the joint weight was so low. Take a look at this one and you'll see that this bar is actually bending like a beam. I think you can see that. It's kind of sagging like a little cantilever beam. So you see the joint has very little deformation. Most of it is in the two beams here. Okay, that's the kind of the desired end state. Okay, so this kind of gives you an idea of the performance of the joint. If we were to put these on our little number line here, where would these things be? This kind of terrible version would be down here, around 10 to the 6, and then as we did successive improvements, the final joint that we looked at would be around 10 to the 9th. Okay, so it gives you some idea of the relative magnitude, right? So several, orders of magnitude different by those little changes. Okay, so those are the principles of good joint design, and we looked at it in this very idealized case. We can't always pull this off because there's other constraints at play generally. But let's kind of take a look at how these things might work in reality. So let's take a look at the hinge pillar and A-pillar joint. This is a particularly important joint in the side frame performance. So this is the hinge pillar down here, and typically this surface here is set by door hinging kind of requirements. The A-pillar exterior surface is set by styling. So these are set by essentially two different organizations within a company. So here is kind of an isolated view here of the A-pillar and the hinge pillar. And if we look at a front view here, so we're going to look at these like this. This is the front view. So here's kind of a line like right here, but now we're looking at it in the front view. The center line of the car is way over here. Here is the hinges for the door, and a line here, and that's right here. Okay, and you can see here that these are not aligning well. So this whole principle of aligning the shear walls, this can happen, and we get a funny little transition here. So this is a kind of a poor joint, and it's due to the geometry of the joint. And what we want to try to do is eliminate this. Again, we want a nice smooth shear plane, more like this. So this is the desired state. When we have this offset here that we showed in the earlier slide, basically there'll just be an awful lot of distortion in that area. Okay, so there needs to be very good coordination between styling, door hinging, and the structural engineer to achieve this kind of a performance. Okay, so this gets to be more of an organizational issue than anything about analysis or structure. Just how can we align these? Let's take a look at another one. This is the going to look at the B pillar and the hinge pillar joint. And we're going to be looking now at the inside of this joint here. So we're looking at this joint like this. And what you'll see is there's a little offset here given by the dimension S. So here's the B-pillar section coming down here. That's this and this. And then the rocker is here, right here. But on the inside surface, which we can't quite see in this picture, there's an offset between this wall and this wall. Okay. So again, this is a case of not aligning the shear walls. And there's good reasons to have to do this, not good structural reasons, but sometimes for packaging or manufacturability, this kind of a situation occurs. And let's take a look at this in the view that we have here. This will be another little animation here. And there's a little offset here. That's this, that you'll see. And you'll see that area kind of light up because it's deforming an awful lot. And causing a relatively low joint rate. So you see that area, lots of flexibility occurring as the loads are being applied down this surface, and they're trying to be reacted along this surface, and that causes a lot of deformation there. Let's take a look one more time at that. Okay, so we're looking at that area there. Okay, so we have a couple of questions that we might ask. We know the best case would be something like this, where this is all coming together at the same point. Right, so we've made S equal to 0 here. Okay, so that's kind of like the ultimate. But we can really ask the question, well, how small does S need to be for it to not matter too much? So here's a way to analyze that. And this is kind of outlined in more detail in the book, but I'll just kind of go through the general analysis here. So what we're looking at is this local behavior due to this offset. And we know we're going to get a lot of deformation there. So what we're going to do is view the rocker as kind of a loaf of bread, and we're slicing the loaf of bread up into little pieces here. And so that's here, here, and here, and here. And that along that, as we load this here, there's going to be loads being applied by this hinge pillar surface along these little slices of bread. Okay, and those slices of bread will distort, and that's what causes the joint to be not very effective. So here's a kind of a picture of the little slice of bread. It's a section of the rocker, and it has this offset in it. And again, the slice of bread is kind of one unit into the page here. So we're not looking at the whole rocker. It's almost like a little beam framework here that we're looking at. Okay? And as we push down here with a force, we get a deformation here. And if we take the ratio of the force to the deformation, we get a stiffness, and we can model that as a little stiffness. Okay? So one of the issues that we need to know is, well, how stiff is this little slice of the rocker? And we can imagine that if the rocker kind of looked like this, and we're pushing here, it would be pretty flexible, versus if it looked like this, and we were pushing here, it would be much more rigid. Okay, and this is we would prefer this case. Okay, but what we want to ask in this little analysis here is, how does the overall stiffness or joint rate, the K of the joint, depend on this little offset? Okay, so here is kind of the steps in making this model. We saw we took the slice of the rocker. We could model that, replace it with just a stiffness value. Here is our hinge pillar that's relatively rigid. It's kind of pushing down on these little springs as we apply a load here, and then we can model that as a joint stiffness, K joint. Okay, so that's the steps of this analysis. We're kind of jumping over all the details. The details are in the textbook. So what we're plotting down here is the joint efficiency. How stiff is this joint relative to the section properties? And what we're doing is looking at it for an offset S here of 10 millimeters, 5 millimeters, and then a half a millimeter. This half essentially means that we're aligning it, that we've achieved this condition here. Okay, the metal thickness. Okay, so you can see that even a 10 millimeter offset really degrades the joint efficiency down to 40% or so. Getting that down to about 5 millimeters gets it to 80%. Okay, so that's pretty good. So this is kind of, we could say this might be acceptable from a structural standpoint. We know that there's some reasons to do these kinds of things. If we could achieve 5 millimeters of an offset, maximum offset, that would be, relatively good. We can do better than that if we zero it out, but maybe that's a point of diminishing returns. Okay, so this is just kind of an idea of the relevance of even these kind of little details in how these joints come together. And I'd like to show you a kind of a recent description of this. This is from the Great Designs in Steel Conference. I would recommend you Googling this. This is a yearly conference that the steel industry puts out, and OEMs kind of talk about their latest designs, and the presentations are free, and there's really no registration required to get these. So I would recommend you taking a look at these. This is from the most recent. This is the 2019 Acura RDX. And what we're looking at here is the side frame. We've kind of been looking at particularly these joints here, the B-pillar to rocker. And here's the center pillar, that's this one. And it's showing the condition that we just talked about. So there's this little offset here, and they're kind of indicating that this has got this kind of skewed load path, a jiggle-joggle in it that isn't so good. And then here is now their new version of this concept. And you can see right here that what they've done is align the shear planes for the B-pillar and the rocker. Okay, so the exact good principles that we talked about, very difficult to achieve like they have done here. Here is another example. We talked about how hard it was to get a nice smooth transition from the A-pillar to the hinge pillar. So you see they've achieved that on this 2016 Honda Civic. And again, good coordination has to be done between the hinge surfaces here that establishes this and the exterior surface that establishes the A-pillar joint. So really, really nice job there. You can see the same kind of a thing, smooth transition between the B-pillar and the rocker on the exterior surface here. Here's the Cadillac ATS example. And one that I really want to point out here is this idea where we have a joint here and here, and we said that we're going to have some high loads being applied. Even though we've made this width really large, we'll still get relatively high loads. We talked about using beads to do this, and you can see what they did was use some bulkheads in order to take those loads. Very effective. In the next slide, we're going to be looking at this area of this design, and we're again looking at the Honda Civic in this case, but here is a joint between the hinge pillar and the rocker, and you can see that internally they have this nice transition here where they're using bulkheads in order to do this. And again, imagine loads here and here when we apply a moment up here. So now they have a nice load path at the back side of the bulkhead, and at the front side they've closed it out. Same car, Now we're looking at a little different joint. So this now is the hinge pillar area. So this is the hinge pillar. That would be up here, and the rocker. And you see a pretty large offset here. Okay, so that part is not so good. But you see this kind of thing that looks like fingers coming out here. This actually extends down. This point here is here. This point here is at the flange. So there's actually continuing this down so that internal to the rocker there is this continuous shear wall there. Okay, so again, very, very good applications of some of the principles that we talked about. So we have not talked very much about this out of plane bending. Here's just an example. This is far less important than the in-plane bending. That's where you really have to be careful. Out-of-plane bending is important for some conditions. This is showing the rocker here, and this is showing maybe a seat cross member that goes from side to side. So this is kind of one way to do this, and we kind of visited this earlier when we were looking at good welding principles. So this was the one with the weld in peel, so not a very good joint. Here they've kind of tried to align the shear walls between this section and this section, so we get a much better joint as well. Okay, so I think now what we've been kind of thinking about are things like these physical joints. Right? There's a beam here and a beam here, and here is a connection between the two beams. Right? So we can kind of isolate them, we can take them apart. Really, we can have an effective joint whenever we have a large discontinuity, even if the beam is continuous. So here we're kind of illustrating a kind of a continuous beam here. So there's no physical connections here, joints, but because we have a curve here, because we have a kind of a large change in shape here, these effectively act like joints. And remember, all a joint means is we have a large amount of localized deformation occurring. So this would be kind of a way to model this particular thing with a set of beams, and then those are connected by joints at the large discontinuities. Okay, so we're going to look a little closer at this. We're going to start by looking at this idea of the discontinuity and how do we handle that. So here is a simplified design of a cantilever beam. So this is the initial concept. So presumably we've kind of sized this section in order to do what we want. But then someone says, well, we need a clearance. So here is a potential design where it's kind of designed by clearance. Okay, thinking here is kind of like, here I need a big section with a high moment of inertia. I need a big section. This is as big as I can make it. Here's another. This is as big as I can make it. This is as big as I can make it here. And then finally I reach the object that I need to miss. So I say, well, here's the biggest clearance or biggest section I can have, and I kind of go down, and then finally, as soon as I can make the section bigger, I make it bigger. Okay, so that's what we mean by design by clearance, and it makes some sense because we're making the beam as big as possible wherever we can. But what we've done is we've introduced effectively a couple of joints, because where there's these big transitions, they're going to act like a flexible joint. Okay? So even though we have a large moment of inertia here, and as big as we can make it here, we're kind of losing it where we made this very sharp transition. A much better way to do that is to make a smooth transition, even though, for example, right here, we could potentially have a larger cross-section, but what we're trying to do is not introduce this localized deformation behavior. So the question is kind of, well, how smooth is smooth? So here's several alternatives that were modeled here, and this is again, back to our little cantilever beam here, but now maybe the clearance envelope is this right here. So we could go right up to it and then go down like that. That's 90 degrees. We could do 45 or a 1-to-1 or a 1-to-3 or a 1-to-4, 5 here, something like that. I think it's 5. And here's the results. So this is the stiffness as measured at the end of this little cantilever beam, and you see that the kind of the most stiff joint is this one that has this kind of a transition. So that's the recommended value. Here's 2-to-1. So for every unit up here, I go over 2 here. Okay, so that would be the recommendation for what is a smooth transition, and you don't want sharp corners either. You want to radius these things, and that will give the best performance because we've kind of minimized the effect of this added joint. So let's kind of look at one other type of a effective joint, and that's just a beam with a curve in it. So here's a roof rail to an A-pillar, and let's say that's made out of a tube, out of a hydroform section. So this is one piece. But because it has this geometrical transition, it's going to act as if there's a joint there. In order to see that, let's take a look at this little plastic model here. So it has a curve in it. And what I'll be doing is applying a moment here and here. And even though this is a continuous structure with no physical joint, what you'll see is a lot of deformation occurring right in this central region. So here, when we look at it this way, you'll see the large amount of deformation that's occurring right at the transition. Okay, so making radii in structures is important. I think intuitively you can kind of understand that it's going to be a function of the radius, how sharp is the bend. But what's happening here, if we just look at this little radius section, as we apply a moment here and here, you saw that the sides are kind of puffing out, and the top and the bottom are kind of being sucked in this very large amount of distortion. So let's just see how we can analyze this phenomenon and see what parameters are important to it, and then maybe how we can mitigate some of the problems. So here is a thin wall section applying a bending moment at either end, so that the stress distribution is going to be compressive at the top and tension at the bottom. Okay, and again, this is thin wall, so this is a hollow section. So if we just kind of break out this top part, just one metal thickness in the bottom part, that will look like this, and the bottom look like that. Okay, so we have this compressive sigma at the top and a tensile sigma at the bottom. Okay. Now let's kind of look at the top part. So we're going to take this and look at the edge. So here's the radius of curvature. Here's a little element ds that we're going to be looking at. And we know that we're loaded along here by an amount, so call it P, which is sigma dA. Okay, so now we're going to kind of just break out this one little element that we've been looking at. So we just from geometry, we have a little triangle here. So R times the angle, very small angle. So the sine of the angle is the same as the angle. That's given by the base of the triangle here. Okay, so that's from just pure geometry. Now we're going to put this little element into equilibrium. So we saw that we have a load P occurring here, and its angle is d phi over 2. So here's d phi over 2. That's why it appears here. And then same kind of thing over here. Just that little angle d phi over 2. And we can kind of see that there's a downward component with each of these, right? If I really kind of make this a lot bigger, we have a downward component and a downward component here. So something has to be pushing upwards on it, so we're going to just put a vector in there that's d capital F. We don't know where that's going to come from yet, but we know that just from the free body, it has to be there. So here is the free body. So we sum forces in this direction. So that dF has to equal this little vector here plus this little vector here. So they end up being equal to this. But we know that d phi we can get rid of. That's going to be ds over r. So we just replace this with ds over r. And then we get this final relationship, which is the radial force per unit of length. So here's a df, here's a little unit of length that it's being applied to, equals this load, this compressive load, divided by the radius of curvature. Okay, so let's kind of draw this. So here it is. So we said that for every little element here, we have a little amount of force being applied to it. That's given by that. We're going to call that W. So it's got units like newtons per millimeter. So that says W, and it's all along here. As long as this has got a curve to it, we have to be generating that little W force. And then here is the loads P at the ends of it. Okay, and we analyzed the upper plate, which is in compression, but we know the lower plate has to be kind of exactly the same, with the sense of all the loads just being reversed. So this is in this direction. Okay, so where do these W's come from? What they have to come from is the web in compression. So remember, we kind of drew our little section like this, and we were analyzing the top and the bottom, but now we know there's a web here, and that web is what provides these little forces. Okay, so for this force pushing upwards, the equal and opposite force on the web is pushing downwards, and kind of the reverse on the bottom. So you see that the web is being compressed, right? This is pushing up, that's pushing down. So the little web is in compression. And we know whenever we have a thin wall structure and we have compression, that things will tend to buckle, and that's exactly what happens. But one way to mitigate that is we can put beads in the section, and we'll want those beads to be in the radial direction. So they're kind of pointing towards wherever that radius of curvature converges. So this is how to make a kind of a curved section like this more efficient, even though it's not a true joint. You know, we don't have a physical connection because of its discontinuity, because of its, basically radius. That's what we are trying to mitigate here. And the bigger the radius is, the better. The smaller it is, the larger these little forces will be because of this expression here. Okay? And I don't have a good example for this in automotive construction, but here is one in aircraft design. So this is looking at where these wings go, kind of up above the fuselage here. And you can see this area here, thin wall structure, and you can imagine that the wings there's a big bending moment here. So it's loading it just like we looked at. Here's a radius of curvature of that area. And then here are the beads that they've added to improve that. Okay, so let's just summarize where we've been with this little discussion. Remember what what motivated this was we know that joints are really important for the overall performance of the side frame. We had described those as just a number, the joint stiffness, and now we have some ways of achieving that joint stiffness, important geometrical kinds of things we can do to joints. Okay, so number one is align the shear walls. So that's what's being shown here. That's the most important. Secondly, radius the corners. So we're trying to make this wider here than up here. Provide some kind of reaction for the compressive loads. So we know we're going to have a compressive load here. We're showing a bead here. It could be a bulkhead inside that would react those loads. Stabilize the plates for shear and compressive buckling. So that's here. And again, we used a bead here. We saw how some of the real car companies would use they would put a bulkhead in here or a doubler to thicken it up. Avoid sharp transitions. So that was the idea of kind of having smooth transitions. Even though the size of the section might be a little reduced, what we're doing is avoiding the addition of an effective joint in that transition. So that's why that's important. And then if we do have beams that are curved, we want to maximize the radius and then add these radial beads to prevent the web from buckling. Okay, so I think that's achieves what we're trying to look at in this section. Where are we going to go from here? What we've done is use the systems engineering process to flow down requirements for bending. And what we're going to look at in the next few sessions is doing the same process, but for torsion. Okay, so that's where we'll be in the next couple of sessions, and we'll see you then.